Bergson, the holographic theory of mind. Continuing, we're looking at the principle of least action, which, as Sabina noted, is as near as we have the physics theory of everything. But in reality, it's a physical model of nothing. But we'll be looking at the historical origins, the birth of a mindset. And that mindset, we've got more zero time, more zero basis for a theory of consciousness, and a very strange dilemma for physics brought on by themselves. We're at the core of the origin of what is considered scientific explanation. So Sabina did a recent video on this, the principle of least action. It's a principle at the core of Newtonian mechanics, quantum mechanics, general relativity, even Maxwell's electromagnetism. It's unquestionable, foundational, a concrete block and a foundational mindset set in cement. Bergson, we've seen, made a general critique of mathematics as far as the intrinsic source of its inadequacy to capture physical reality. Had Bergson bothered to address the principle of least action specifically, well as a myriad of others equally in the foundation, for example, Euler's identity, Dirac's principle, Noether's theorem, the magic of the radian, SI units, well, he would have spent a long time discussing. But it's worth it to show that his general critique was applicable to all these things. So let's see. Sabina gives a slightly different history. This is the history I've seen. Huygens, around 1659, addressed the tautochron or isochrone curve. Now this is the curve for which the time taken by an object sliding without friction and uniform gravity to its lowest point is independent of its starting point in the curve. So we've got our little balls going down the curve there. And here's the deal. Whether we start the ball here, or here, or here, or here, they all end up here at the same time. So they all go at the same time. Here's a picture of it all sliding down. Notice they all hit the same place at the same time. The curves at the top there are the acceleration curves. So obviously the blue ball has the sharpest acceleration curve, the yellow the slowest acceleration curve. Now Huygens showed this curve is a cycloid. Cycloid is such a scallop form made by a rotating circle. The time the descent showed is equal to the time a body takes to fall vertically, the same distance as the diameter of the circle that generates the cycloid. So if my cycloid was up at the, looking at the top right there, and the time is equal to the diameter times pi over 2, where the diameter is of that circle that would be that line sweeping along making the circle. Now falling is actually the acceleration of gravity, so we can write the equation this way too, pi with g being the gravity in there. Now we come quickly to a who's who of the greatest minds in physics and mathematics. Johann Bernoulli, 1697, the dates here being roughly when they did this. Bernoulli used Huygens' solution with a cycloid to solve what's called the brachistochrone curve. Again, what is the shortest time, brachisto being shortest, or curve of fastest descent between point A and B. Again, the curve is a cycloid, but it always starts at a cusp. Notice back to the cycloid there, we've got various cusps. So the curve is always starting at the cusp. It can use a full rotation. For example, if A and B are on the same level, we'd have a full rotation of the cycloid, a big piece of the cycloid curve. Now, Bernoulli published the problem in his journal Acta Eruditorium in 1696, allowing 6 months for solutions to be sent in. And later he had to extend this to a year and a half because he wasn't getting all the responses he wanted. Newton, who was off on a trip, finding the letter and returning from the trip, just after the first 6-month period that Bernoulli had set, worked all night and sent the solution in anonymously. This led to a famous supposed quote from Bernoulli. I recognized the lion from his claw mark, so he saw instantly it was Newton. Now 5 mathematicians responded with solutions. Newton, Jacob Bernoulli, Bernoulli's Johann's brother, Gottfried Leibniz, Ehrenfried Walter von Tischenhaus, and Guillaume de Hoptal. So here we go, all the various guys. And note, definitely you had to have long hair to be a mathematician, apparently. Brother Jacob, to outdo Johann Bernoulli, created a harder version of the Bergson problem. In solving it, he developed new methods that were refined by Euler in 1766, what he called the calculus of variations. The 19-year-old Lagrange sent Euler his own improvements, Euler being impressed enough to use them and cooperate. Hence, this takes us to the Euler Lagrange equations, the Lagrangian and ubiquitous in physics, into the principle of least action. So that's what we'll now look at. But wait 1 second. But firstly, let me note what we've just seen, in my opinion, what we just reviewed here might be the most critical period of thought following Newton's own works, and for throw in Galileo, that's cemented in what we now view as its scientific explanation. That is, the mathematical framework for scientific explanation. So, warning, just 3 slides coming up with a bit of the math behind this form of explanation. So, getting going on the principle of least action. We're going to start with a static curve. Now, I'm going to note before I get going, I'm taking this path representation from Calculus of Variations course by Ross McGowan. Ross is a Scottish guy with a little bit difficult accent to comprehend sometimes, but then again, everybody else is presenting this as an Indian from India, and those guys start at a level of abstraction that's usually kind of mind-boggling and not as concrete as I would like. So I prefer Ross. And as I said, we're going to start with a static curve. That is a rope hanging from 2 pulleys there, and we're simply going to let it drop. So we've got a static curve resulting from the drop of the rope. Now, this is a special case of, say, a motion like a pendulum. We've got a sweeping curve. And we've only got the potential energy in this hanging rope case. In the pendulum case, we got the kinetic energy and the potential energy. We got a maximum potential energy at the top there, a maximum kinetic energy at the bottom. And basically, we have a case where we're transforming potential energy into kinetic energy. This will be interesting. We'll bring this in later, this transform or trade-off of potential energy to kinetic energy and vice versa. So again, just potential energy there. What we're going to do is linearize this curve, break it up into a series of linear segments. So there would be our first little segment, the purple segment, a line, not getting all the curve, not getting the total path of the curve, but getting it. The M represents the mass of that rope, and the potential energy, the equation up there says that it's a function of the mass of the rope, the force of gravity, and the height of the rope. At any point along the rope there, you're going to have various changing function depending on the height and the movement along the x-axis from 0 to L, the length of the rope down there along the x-axis. And so we're going to take that little segment and we're going to treat it in terms of the Pythagorean theorem. A change along the x, a change along the y, and so we have our little triangle there, and the Pythagorean theorem, dx squared dx plus dy squared. So the argument and limit, when the curve segment is small enough, it will in fact be essentially a straight line. That's what you have to assume, accept here. And then we're going to add up all these tiny segments. That is, we're going to integrate all the little segments we're going to create, and they're going to be smaller and smaller segments, and we'll integrate them all into one big total. And of course, the little m's, just showing that equation there, the little m is going to be a function of the big M, the big mass of the rope, the length of the rope, per the distance we're taking it from by each little purple distance there. And any particular chunk of mass then that we're breaking it up to will be, well, will look like that, m over L for the distance. And so what you're going to get is basically the use of the Pythagorean theorem there, ds squared, plus we're just going to divide that by dx squared, and we get the other expression. I'm not going to spend time explaining each of these little algebraic moves. That's really all they are. We end up with an expression for ds, the change of distance along the y and the x-axis there, the change of the mass, and a resultant expression, E of P, the potential energy of the rope, taken from 0 to L, all those little segments across the whole of the rope. Now that expression then ultimately is, rewritten a bit, is the potential energy of the rope. So we got the potential energy of the whole of the hanging rope. And now we're going to want to know or show when this potential energy is minimized, when we have the minimum possible configuration potential energy. We'll come back to the minimizing that potential energy for the rope. Let's take another look at a different view, total time, in this case for the Christochrome. Minimizing, how do we get the total time? Again, we're taking that curve that the ball is falling down, breaking it into little segments, like our little purple segment there, with the change of the segment. We've got the potential energy, E sub P, the kinetic energy, E sub K equals 1/2 mv squared. We combine those two formulas into an expression for the whole, and then we're simply going to take it with respect to the change in the little distance over the change of time. We're going to do some algebraic manipulation that looks roughly like this. Throw in our Pythagorean theorem there, ds squared equals dx squared plus dy squared. Again, making our little triangle up there. And with a little bit of algebraic manipulation, I've decided not even to worry about particularly explaining these, so to watch it happen. We're going to end up with an expression for the total time, which looks fairly fearsome, but it's only the interval from 0 to x1 of the full distance with the of that curve, with it expressing the total time thereof. So given we have the equation for total time, we want to find the minimum value of this function. Now a note here. Now in the calculus of variations, as Euler invented it, this was coined as a functional. In a regular function, we're mapping numbers to numbers. We have a little equation there, y equals x plus 1. So if x is 3, then y equals 4. But in other words, we're mapping x is 3 to y is 4, mapping the numbers. In this calculus of variations case, we've got functionals. We're mapping a number to a functional, y of x. That is, as things change, as y changes, the vertical dimension along as the x-axis changes. So we have a functional. Just an interesting thing that was introduced. For the hanging rope, as its value changes on y and x, the value of the potential energy changes. So finding the minimum becomes a long string of simple derivative rules and trigonometric identities. We'll glance at it here. This is what it would look like. This is quite a string of derivative rule applications of trigonometric identities, getting down there toward the bottom. What do we end up with? Well, in the end, we end with the parametric equation for, yes, a cycloid, which is exactly what the solution was back then. So we have the parametric equations for a cycloid for this curve. So this is the form of path that gives the minimum time for our little balls rolling down there. Was this Newton's overnight path? Interesting. Ross McGowan didn't know. I don't know, but it would be something like this. Something awesome, no doubt about it. In one night, it took Bernoulli a couple of weeks to figure this out. So this is all beautiful, but you cannot linearize circular time. This is all built on this fiction, exalted into an ingrained, unthinking, unquestioned reality. But to finish the least action story, it's going to be just too much to take us through forming the Euler Lagrange equation in detail. So just a few futures to remove any mystical aura. First, the S. Now we saw our equation for the potential energy, the total potential energy of the rope, P. And we can just generalize this as S. That is, we'll call S a general function from x1 to x2. And the idea is it's a quantity across 2 points, x1 and x2. And it's a function f dependent on x, y of x, and y derivative of x. It is the rate of change of y with respect to x. And it's something we want to minimize as a total quantity. No, the delta S. Well, we'll see more on this in a bit. Second, just a sketch of the route to Euler Lagrange. Back to our rope. Now, we could imagine that rope being pulled down. So imagine the original position of the rope is the blue line with segments 1 and 2 broken down, and then it's going to be pulled down along the y-axis to the position in the purple 3 and 4, with the little delta y between the purple and the blue being the amount we're pulling down, dy. So, or delta y. So what you're going to have here is a change of position. The rope's going to change position, obviously, as it drops down. And you're going to get simultaneously, obviously, a change in slant or gradient. You're going to have the new position 3 relative to 1, the position 4, the purple line relative to the blue line. So we're not changing. I'm not showing here the equations for the change of position. Right here, we're showing the little equations for the change of gradient. And I'm skipping several steps that Ross McGowan takes one through, and very nice explanation of the little algebra involved. But those little equations, 1, 2, and 3, 4, are expressing the change, the original gradient, like for 1, and the change of gradient from 1 to 3, and the 3 expression, etc. So the idea is we're breaking down the change of gradient into little segments. But remember, the idea is to always get back to equilibrium, to the minimum potential energy. So the Euler Lagrange, we're going to have the change of position with the change of gradient, but we want that set to 0. So this is ultimately the equation for Euler Lagrange. The first expression, delta f over delta y, expresses the change of position for that function f. And then the second set of terms there after the minus sign are the change of gradient involved, and all that's set to 0. And if you put a little delta y in front of all that, you'd have the little change in position we just saw, the delta y, the change in gradient and pulling down the rope. And then we have the Euler Lagrange. It has to be set to 0 to minimize and bring back that rope potential energy to 0, or the Lagrangian to 0. Now third, then the Lagrangian. Well, we can look at motion under gravity. We're going to drop the garbage can to the earth in a gravitational field. And we have the Newtonian equations, F equal ma, and we throw that in terms of gravity, g for the gravitational force. It's dropping, so we have the minus mg equals m double derivative, second derivative of y, which is acceleration, so mass times acceleration in that terms. And the x position, there's really nothing happening, so it's all going to be set to 0. So the equation for the drop of the garbage can in the gravitational field was shown right there in the green. And that's the Newtonian equation. And we're always asking then, well, what gets minimized and what is stationary? Well, this brings in the Lagrangian. The Lagrangian is defined as L equals T minus V, where T is the kinetic energy, E sub k, and V is the potential energy, E sub p. Well, in other words, the kinetic energy minus the potential energy, that's Lagrangian. So L is a constant difference between the kinetic energy, T, and the potential energy. And in our rope terms, this is what it would, well, in our, I'm sorry, not the rope, the dropping the garbage can, the L, the equation, the function, is L is 1/2 m, and et cetera, for the equation for the drop of the garbage can. And then we have our Lagrangian, same form we've just seen. Notice we're throwing the L as the function, dl over dy. And so L becomes the function we put in Euler Lagrange. And we apply a bunch of differentiation rules to get the equation of motion that keeps L, that is T minus V, at a minimum. So nature is always trying to minimize L. That's the idea. Lagrangian is that which nature tends to minimize, attempts to minimize. And when we do that operation, applying all the differentiation rules, out comes, voila. That is, via Euler Lagrange, we get the same answer as we would using Newtonian mechanics. So we can derive the Newtonian equations of motion via the path description, shall we say, of Euler Lagrange. Now, fourth is Hamilton's principle. And this is it. An object travels in a path such that the Lagrangian is stationary. Now, stationary means it's minimized. And there's the equation integrating the Lagrangian L from t0 to t1, so over time with respect to time. Now, Sabina presents it as such. Instead of the Hamilton I, that we have S for action, but exactly the same formula. She's got T minus V. We just remember L is in fact T minus V. So that's S for action, which is that integral expression for the Lagrangian, keeping the Lagrangian minimum over that path. Again, we can look at it in the pendulum terms. We have the max potential energy at that point, the minimum potential energy at the bottom, but simultaneously it's the maximum kinetic energy. That is, as the potential energy, V is decreasing as it drops, it's the kinetic energy, T, is increasing. Or we've got this sort of strange transformation of potential energy to kinetic energy and vice versa. And for conservative force, T plus V equals a K. That's a constant. You're always having as t grows and v decreases, you're always equaling k, or L equal t minus v. Now the principle of least action, then, fifth, is we have ds equals 0, is that we're simply taking the derivative with respect to the whole path such that it's 0, and this is the optimal. That is, we have the best possible path to minimize energy. Leaving aside the math now, we could throw the garbage can in a gravitational field, not just drop it. So we throw it. And it's going to take a path. The path of least action is a parabola. Now Sabina notes an interesting question. Again, she says, note how weird this is. It's not that the rock, I use a garbage can, she uses a rock, tries all possible paths, it just gets on the way and takes the best one at first try. Like it knows what's coming before it gets there. Like study Lagrangians. And she says, yes, the principle uses an integral into the future. Note that we're integrating to TB, the time point in the future. How do we explain that? Well, it turns out there's another way to express the principle of least action. One can mathematically show that the path which minimizes the action is that path which fills the Euler Lagrange equations. For example, the Euler Lagrange equations in the garbage can example, just falling, give Newton's second law. Now, we've seen that. We just saw that the derivation, throwing the problem into the Euler Lagrange produces the law of motion, Newton's law of motion for the falling object. And the Euler Lagrange equations for electrodynamics are Maxwell equations. And the Euler Lagrange equations for general relativity are Einstein's field equations. And in these equations, you don't need to know anything about the future, so you can make this future dependence go away. But you can't just make it go away. Now you have no explanation of the path. And you've thrown Huygens, Bernoulli, Newton, Euler, and even Lagrange into the garbage can. You've thrown away the solution to the brachistochrone, to the Tautochron curves. You don't know how they work anymore. You're back to ground zero. What's the problem? It's because this is all only mathematics. It is not a physical model of the motion. For example, if we brought back the ether, how an object might be interacting with and in an ether medium, such that that parabola is affected. Other examples of where we have the same problem. E equals mc squared. It's a math equation which drops out of the Lorentz equations of special relativity. Just a mathematical derivative, but it's not a physical model of mass energy conversion. Yes, it works. It describes something, predicts something, but it's not a model. Or E equals h nu. Again, assuming an ether. What's the meaning of h? Where the physical meaning then would be of h, the strain in the ether medium, the energy needed to impart to it, needed to initiate a wave, given the ether's elasticity and density. Or, quote, time, unquote, changes in special relativity. That is, we'd actually have a physical model of the processes underlying the increased lifespan in muons. It is a physical model of the retardation of aging, of the physical processes involved in aging and why they're retarded. Not just an equation group or transformation within the Lorentz transformations and nothing more. In fact, I can't quite resist this because I'm just simply not comfortable with this phenomenon. Because one wonders, is this lack of physical grounding in Newtonian mechanics itself at the heart of Lathwaite's problem with gyros. Remember the gyro happily precessing long after its metal platform is extended past its tipping point. Stop the gyro, we see all the weight that would be necessary to have needed to balance it. Lathwaite was driving toward this difficulty. There's something not grounded in Newtonian mechanics. But this was the great and alluring turn to pure mathematical abstraction, the great implicit agreement of all these brilliant minds, and no doubt they were brilliant, on what became physical explanation. And it has all become so complex, so intricate, so fascinating to the intellect. It simply cannot be put in its proper place, in its true value as an explanatory mechanism. Now, Sabina flips on throwing this future dependency away, as well as a chunk of history. There's that darn quantum mechanics and the measurement problem. She notes the wave function has the particle exploring all possible endpoints and paths to them. And of course, the problem that we see is from the classical to the micro to the quantum. How do we do that transition? How does a garbage can do this? It doesn't. But a measurement collapses all these paths to just one. Now, Feynman, she notes, said, well, rather than doing this observational measurement and collapsing the path, you just calculate the probability for the particle to go to one point, that point that it selected, by summing over all the paths that go there. Thus, and you get the Feynman path integral, which is, again, essentially using the principle of least action. The future time dependency is still there. Still got TA to TB. But not a worry, she says, because the particle explores all the paths anyway. But, she notes, but it doesn't. It takes the one path. So, she says, so maybe the reason we have the measurement postulate is that we don't take this dependence on the future, which we have in the path integral, seriously enough. Let's say this is a bit of coping, because this is nice. But now you put the basis of all physics in a mystical precognitive knowledge of the future. And the way physics is going nowadays, I'm quite sure they'll like this. They'll explore this. I'm sure. In other words, this is the depth of the now of the current confusion. The depth now of the current confusion. All of this rests on this basis, that we can linearize circular motion and do this with infinity of linear segments, such that each little tiny segment of the curve is reduced at limit to a straight line. Or that we can do this with any motion, that the motion can be divided into a series of ever smaller lines or segments. And again, at limit, the motion is now a static point. Thus, a determined value can be derived. And as we've noted, in the context of Zeno, in the paradox, there is no interval, no matter how small, in which Achilles is not constantly moving. No fixed value then can ever be determined. But this entire approach flies in the face of this fundamental problem. As we've noted, for Bergson, motion is indivisible. It cannot be divided infinitely into a series of static lengths. It is an organic continuity, like a melody, each note, quote, or instant, permeating the next, organically. Again, as we've noted, were there ever fixity, the universe would be frozen, never again to change. So you've got an intrinsic trade-off, no determined values for constant change in this universe. This just is simply being ignored. It's so straight out. On this indivisibility of motion, I put it as such. Motion is non-differentiable. One can beg a point of definition here. In calculus, a non-differentiable function has a specific meaning. it comes to an inflection point. It is a point at which there is no change. This is curious. What is the limit, the logical end of the operation of taking smaller and smaller intervals? Well, it's a static point, a mathematical point, thus a point at which there is no change, same difference. This says in reality, no motion is differentiable. Yes, it seems a logical contradiction at the foundation of calculus, conveniently ignored because it is such a powerful tool. It all works, quote unquote, so wonderfully well. This powerful framework with this Lagrangian, its principle of least action, the heart of our science. Where does the contradiction in space come home to roost? Where does this fiction, this abstract non-reality, meet its demise in the concrete world? Clearly, when faced with the problem of consciousness. Why? Because to solve the hard problem, to account for qualia, to handle common sense knowledge, to understand the relation of consciousness to cognition, we require the true indivisibility of the transformation of the universal field, as we've noted with Bergson's model. We have a holographic field indivisibly transforming the brain, a modulated reconstructive wave passing through it, and specifying a past transformation of the field. You cannot have such a model without the indivisibility of the field. That is a field where there's of the motion of the field. That is where there are no instants falling into the past, into the non-existence, quote unquote, of the past. You have to be able to specify the past transformation of the field, and that is scale of time, e.g. the buzzing fly. That current physics is the starting point, and this is the ubiquitous view, with its mathematics based in the classic metaphysic and its fictional zero time, that is to start for the theory of consciousness. It's not possible. All this is simply relative motion. Treating motion as simply a change of position, which is all mathematics is intrinsically capable of doing. Relative motion. I can move the object across the abstract continuum of points, positions. Or I can move the continuum, or the coordinate system, beneath the object. The quote motion, unquote, of the first is now rest in the second. Motion becomes rest simply on change of perspective. That is, real motion is lost. So we were talking of Euler, Newton. You'll never hear folks like this, these physicists, discussing this. But if there is absolute motion, is it possible to persist in regarding movement as nothing but a change of place, change of position? We should then have to make diversity of place into an absolute difference and distinguish absolute positions in an absolute space. Newton went as far as this, followed moreover by Euler and others, the mathematicians. But can this be imagined or even conceived? A place could be absolutely distinguished from another place only by its quality or by its relation to the totality of space, so that space would become, on this hypothesis, either composed of heterogeneous parts or finite. But to finite space, we should give another space as a boundary. And beneath heterogeneous parts of space, we should imagine an homogeneous space as its foundation. In both cases, it is the homogeneous and indefinite space that we should necessarily return. We cannot then hinder ourselves either from holding every place to be relative or believing some motion to be absolute, that is real. And I've noted before, take our little organically unfolding rose as a real absolute motion that cannot be relativized. That is, you can't send an observer by, an observer watching the rose, and tell that observer watching the rose that he's actually in motion. Therefore, the simultaneity of parts he thought he observed of that motion of the rose are declared non-simultaneous by the other observer. That's not going to happen. It can't. He goes on, it may be argued that real movement is distinguished from relative movement, and that it has a real cause, that it emanates from force. But we must understand what we mean by this last word, that is force. In natural science, force is only a function of mass and velocity. It is measured by acceleration, F equal ma. It is known and estimated only by movements which it is supposed to produce in space. One of these movements it shares their relativity. Hence the physicists who seek the principle of absolute motion and force, so defined, are led by the logic of their system back to the hypothesis of an absolute space, which they had first desired to avoid. And such is Einstein. He took acceleration to indicate an absolute force. And he ends with a curved, bounded absolute space. So it will become necessary, Bergson goes on, to take refuge in the metaphysical sense of the word and attribute the motion which we perceive in space to profound causes, analogous to those which our consciousness believes it discovers within the feeling of effort. But is the feeling of effort really the sense of a profound cause? Have not decisive analyses shown that there is nothing in this feeling other than the consciousness of movements already effected or begun at the periphery of the body? Have not decisive analyses. He's referring to, in at least one case, time and memory, time and free will. In his treatment of pain and feeling, that is, the feeling of increasingly greater force applied when lifting successively heavier weights. This feeling of force resolves, in reality, to successively more muscle groups being brought into play for each weight. Greater the weight, more muscle groups. So, in other words, the notion that there's some profound force other than the motion dissolves into the pure recruitment of more and more muscle groups. It is in vain, then, that we seek to found the reality of motion on a cause which is distinct from it. Analysis always brings us back to motion itself, not relative motion. But this is all lost to him beyond the current crop of philosopher-physicists. Which brings us to this as a postscript. Google engineer suspended after saying artificial intelligence has feelings or thinks it's come to life. Or, in other words, is the AI sentient? Which he thought. Sentience. What we're brought to. Google, he said, no. It's just a very good chat program. Or it's good coding. No sentience. But the discussions I observed around this, pro and con, are clueless, lost. And in truth, I kind of think only the few hundred or so souls that have followed a good chunk of these videos actually understand the deep set of issues. Time, subject and object, time scales and variance laws, the origin of the image of the external world, the storage of experience, whether or not it's stored in the brain, conscious cognition, that is, the relation of consciousness to cognition. The confusion is so vast. We saw questioning in the last one on information, number 69, on whether there's even a physical basis for perception. It's that lost. Why? All awareness of the critical role of time in the nature of sentience, gone. Gone with Bergson. Why? Well, we've been looking at the historical origin, the great meeting of minds that, in all their brilliance, and I'm not deprecating their brilliance, decided that they'd found the new framework for scientific explanation. So the mysteriously magical, alluring, explanatory power of mathematics that in fact rests on zero time. Next, we'll see. Till then, signing off.